So let's take a look at gas exchange in the lungs and gas exchange in the end tissues, the somatic tissues. So in order to do this, we can use a train analogy. So here's the train platform on the left-hand side, here's the train on the right, and in between the two is the warning track that separates the train platform from the actual track. So in this situation, this example, we're going to start with the lungs. So the lungs is going to be the train platform, and the bloodstream is going to be the actual train, specifically the red blood cell. So how do we get oxygen from the lungs all the way down to the muscle cell? So when we inhale our breath, we're going to have a high concentration of oxygen. The concentration is going to be higher than the concentration of oxygen in the red blood cell. So oxygen is going to diffuse down its concentration gradient and is going to bind with a protein called hemoglobin that's on the red blood cell and in the red blood cell and form oxyhemoglobin. You'll notice the hemoglobin turned bright red because when there's an oxygen atom or multiple oxygen atoms attached to hemoglobin, it turns bright red. So now that oxygenated hemoglobin is going to go for a ride and is going to be on the train for a little while. And now we end up down at the muscle cell in the tissues. So the oxygen will separate from the hemoglobin, and the hemoglobin will become dark again. And now, because there's a higher concentration of oxygen in the red blood cell than there is in the muscle cell, because you have to remember, in the muscle cell, we're doing cellular respiration, and we're constantly needing a constant supply of oxygen. So the oxygen will diffuse down its concentration gradient and enter into the muscle cell. Now, as we said, we're doing cellular respiration, so CO2 is going to build up in the muscle cell, because remember, glucose plus oxygen will give you CO2, H2O, and ATP. So CO2 is building up, and we need to get rid of it, because if CO2 builds up in the muscle cell, or muscle fibers as they're called, it will combine with water to form carbonic acid, which will then lead to acidosis. So we need to get rid of that CO2. So there are two ways we can transport CO2 back to the lungs. So in the first way, there's a high concentration of oxygen in the muscle cell, low concentration in the bloodstream. So CO2 is going to diffuse down its concentration gradient and is going to bind with hemoglobin. And we form HbCO2. And you'll notice that the hemoglobin still stays pigmented darkly. That's because it's not oxygenated. Okay, that HbCO2 will then go for a ride back to the heart, back to the lungs, and now we'll separate and back into CO2 and a free hemoglobin. And that CO2 will then diffuse into the lungs, and that hemoglobin will be free to pick up an oxygen. Another way we can get CO2 from the muscle cell back to the lungs is a little more complicated, but it's still totally doable. So again, we have a higher concentration of CO2 inside the muscle cell than in the red blood cell. CO2 diffuses into the red blood cell, but in this case, it will combine with water to form carbonic acid, which is a very weak acid. Now, carbonic anhydrase is an enzyme that will split carbonic acid into HCO3-, which is bicarbonate, and H+. H+ is otherwise known as protons, because if you take a regular non-ionized hydrogen atom, it's got one electron and one proton and no neutrons. If you strip away its electron, it's only left with one proton. So therefore, an H+ is simply a proton. So what happens now? Well, we're going to do this a whole bunch of times because we're producing a lot of CO2 in the cell. And there's a lot of CO2 coming from the muscle cell diffusing into the red blood cell, and therefore a lot of bicarbonate, HCO3-, and a lot of H+ protons building up. Well, let's take a look at the HCO3- first. That builds up inside the red blood cell to the point where it is actually going to diffuse out into the blood plasma, because there's a higher concentration of HCO3- within the red blood cell compared to outside, so it will diffuse out. Now, because it's diffusing out and taking a negative charge away from it, we need to replace that negative charge. this is where chloride comes into play. So chloride will then shift into the red blood cell and it will effectively swap spaces. So from here on out until we get back to the lungs, chloride will be inside the red blood cell and HCO3- will be outside the red blood cell. We call this the chloride shift. Okay? Well, what about that H+? What about that leftover H+? We have to do something about it, otherwise it's going to become acidic and we're going to drop our pH and denature proteins, effectively tenderizing ourselves from the inside out. Okay, well, remember that hemoglobin that got freed up when we dropped off the oxygen in the muscle cell? Well, there's still some hemoglobin, there's hemoglobin laying around. So we take H+ and we bind it to hemoglobin and form HHB. Now this again is not oxygenated, so we're staying dark red. Okay? So we effectively have HHB inside the cells. It's a protonated hemoglobin inside the red blood cell, as well as Cl- and HCO3- bicarbonate is outside the cell. All right, well, let's go for a ride. We'll stay on the train, go back to the heart, and we end up back in the lungs. Okay? And now there's a higher concentration of HCO3- outside the red blood cell than inside, so it will then diffuse into the red blood cell and displace the Cl-, so they'll effectively switch spots. And now that HHB will separate into the proton, the H+, and hemoglobin. And now that proton will then combine with bicarbonate, here we have here, to form carbonic acid, which will then dissociate to form CO2 and H2O. And now that CO2 will diffuse out of the red blood cell into the lungs where you can exhale